All right, let's talk about how to remove a node from a binary tree. And I'm not actually going to write any code right now. I just want to show you pictorially how this is done. Then I'll start you with a bit of code and I'll have you finish it in an exercise. But, let's say, for example, I wanted to remove the node 12. So, now this is going to be a huge pain because 12 is right in the middle of the tree here. And if I try to get rid of it, it's going to leave a bunch of orphans, you could say. So it has a bunch of children, and they have children. It's going to leave an orphaned left subtree and an orphaned right subtree. And so where are they going to go? Well, I can't just add them. I can't just say, okay, we'll go to the grandparent, go to the parent of the thing that they just lost. Because now I have a trinary tree. Okay, I don't have a binary tree anymore. It's supposed to only have a left and a right. So binary means it only has 2 children. So that's not going to work. One thing you could do that some people do is you can make this into a zombie node. Okay, so that's another option. So basically we'll just ignore this anytime we do an in-order traversal. We'll kind of keep it in the tree, but we'll not print it when we do an in-order traversal. If we go to add it back again and we see that it's a zombie, well then we just get rid of the zombie status. So if I then go to add a 12 and I say, oh whoops, I'm at a zombie that's a 12, now the zombie is brought back to actual life. Okay. Problem is, if we keep doing this, we're going to end up with a graveyard. And we're going to have all these nodes that we're not using, and that's kind of a pain. You could do that. This is probably the simplest solution. But it's not super elegant. Okay. Another thing you could do that's a little more elegant, but definitely not super efficient, is to actually take these orphan subtrees on the left and the right and add every single one of their children back again. So I kind of do this, and then I say, okay, well, let me add these one by one. So I go through, I'll add 9 in some order. Okay, this looks here like it must be the pre-order. But I'll add the 9, then I'll add the 5. Oops. Then I'll add the 1. Then I'll add the 6. Then I'll add the 16, which will come somewhere over here. Then I'll add the 25. Okay, so I end up with this tree. So I'll just add all the nodes one by one that got orphaned. So every single node in the subtree that got orphaned. And so I know that the addition maintains the invariant that I want. So that'll definitely work. So I managed to remove something. The problem is I have to re-add every single thing in a subtree, and I could have a humongous subtree. So imagine if I removed the root. Well, then I have to add everything over again. So that may not be the best. Okay. So can we do even better than that? Well, I'm going to follow the book here. The book has a very nice solution that you can look at if you want. This is in chapter 17. So it's in section 17.4. So let's talk about what the book said. Well, the book has a nice philosophy. He says that when you're not sure what to do, think about the simplest case first. So if I look at, well, what if I wanted to remove 6? Well, that's pretty easy because 6 is a leaf node. What it means is it doesn't have any children. So I can just get rid of it. It doesn't have any dependents that we need to worry about. It's gone. Boom. Okay. So that's pretty easy. So we'll say that removing leaf nodes is pretty trivial. Okay. But that's not the only case that's easy. What if we remove 16, for example? Okay, so if I remove 16, well, 16, it's not a leaf node, but it only has one child, 15. So in this case, I actually can make, or sorry, the child was 25. Okay, in this case, I actually can make 25's parent be its grandparent. So I can make 25's parent be the parent of the node I just removed, and it'll be fine. And I could even have an entire subtree below this, and everything would still be kosher because I knew that the whole subtree of 12 is greater than 12. So if I attach this node to 12, well, everything is still greater than 12. I just got rid of one of the nodes that happen to be in its subtree. Okay. All right, so removing leaf nodes is trivial, and also removing a node with a single child amounts to simply reassigning that child's parent to be the node's parent. Okay. So those two cases aren't too bad. The case that's rough is when we want to remove something that has two children. So it's right in the middle of the tree. So like, you know, if I wanted to remove 72, I can't really do what I've been doing. Okay, but here's what I can do. So if I want to remove a child or a node that has two children, then here's what I got to do. So I have to do a few steps. What I'm going to do is I'm going to swap this node's key with the node's key that's the greatest, that has the greatest value in the left subtree. Or I should say that's the greatest in the left subtree. Okay. I guess I should say first, find that node. Find the node in the left subtree with the greatest value. Okay. So let's say, I was removing 72. So here that would be 71. I can follow that simply by following, I start at the root of the subtree, which is 64, and I keep following right branches until I get there. Okay, that didn't take me too long. So this is swap 71 and 72. That's the next step. So you find the node in the left subtree with the greatest value, swap this value with the value to be removed. Okay. So in this case, I'm going to swap 71 and 72. Whoops. All right. Now, because I picked the node with the greatest key in the left subtree, when I elevate that value to this position, I can guarantee that everything to the left of it is less than it, right? By virtue of picking the greatest one. So I picked the greatest one in the left subtree. When I elevate it up here, it's the greatest, so it's going to be greater than everything. There is one problem, though. The node that I swapped in actually violates the condition. So everything except for the node that I swapped in from here is less than the 71. Okay, but this is the thing I want to remove anyway, so that's fine. So I'll just remove it. Remove the value, or remove the key that we want to remove. And it's either going to be a leaf node or it's going to be a node with a single parent. So I can just get rid of it. And either just get rid of it, if in this case it's leaf node, or reassign its parent. So that's the algorithm. Okay. So I'll have you implement pieces of this. It's a little tricky in code. But I'll have you implement pieces of this, and then we'll move on to complexity analysis of all this stuff. Okay.